Let's talk about solving differential equations through reduction of order. If y sub 1 is a non-trivial solution of y double prime plus p of xy prime plus q of xy equals 0, we can find a second solution, y2, such that y1, y2 is a linearly independent set. We just use this formula. y2 equals y1 times the integral e to the negative integral of p of x dx over y1 squared dx. That was hairy and complicated, but it's really not so bad. And to be honest with you, I'm not going to make you memorize it. Function y1 equals sine 4x is a solution to the differential equation y double prime plus 16y equals 0. Use the reduction of order formula to find another solution. Okay, so again, here's our reduction of order formula. And in this case, we get p of x from the general form of the second order differential equation. When we look at our differential equation, we see that there's a y double prime and a y, but there's no y prime in our differential equation. That means that the coefficient of y prime, namely p of x, is 0. So let's plug everything we know into this formula. y1, notice, is going to be our solution to the differential equation. P of x is this coefficient of y prime, which in this case is 0. Okay, so here's our general solution. We plug in y1, our other solution, sine 4x. In this case, p of x is 0, and again, y1 is just sine 4x. So we have sine 4x times the integral e to the negative integral of 0 dx all over sine squared 4x dx. We can rewrite this. The integral of 0 is just going to be some constant c, so we're just going to write that as e to the negative c. And we can write this as, well, we can write sine squared 4x as cosecant squared 4x. I do that because then we can integrate cosecant squared easily enough. Now, c is just a constant, so I can just write e to the negative c as just plain c, because c is just some random constant. So e to the negative c is just some random constant as well. Okay, and we pull that to the outside. So we have this integral. You may remember from first semester calculus, or you've probably forgotten, cosecant squared 4x, the antiderivative of that is negative cotangent 4x. And when you integrate this because of the chain rule, or because of substitution, you have to divide by 4. Okay, so no one really likes working with cotangent. Let's express it as cosine over sine. Notice we have c sine 4x over 4, negative cosine 4x over sine 4x. And that can be simplified because the sine 4x's cancel. Okay, and we're just left with negative c cosine 4x all over 4. So this is just going to be a constant. So negative c over 4, c is just some random constant. So we'll rewrite that as c cosine 4x. So in other words, our original solution was sine 4x. Another solution is c cosine 4x. Or really, we just need any solution. This one is sufficient. So another solution would be y2 equals cosine 4x. Now, to be honest, this one can be solved much more easily using techniques we'll see in the next section. So let's look instead at this one. This one cannot be easily solved. So reduction of order really comes in handy. The function y1 equals x to the fourth is a solution to the differential equation x squared y double prime minus 7xy prime plus 16y equals 0. Use the reduction of order formula to find another solution. So again, given this as our general second order linear differential equation, we see a problem. Namely, this has y double prime in it, and this has x squared y double prime. We need to get it in this form, folks. So let's divide both sides by x squared. So when we take this differential equation, divide both sides by x squared, we get y double prime minus 7 over x y prime plus 16 over x squared y equals 0. And then by comparing these two equations, we can see that our p of x in this case is negative 7 over x. That's what's out in front of the y prime. Okay, so p of x is negative 7 over x. Let's plug that into our general formula, reduction of order formula. y1 again is the other solution. So when we plug everything in, we get x to the fourth e to the negative integral of negative 7 over x dx. The other solution was x to the fourth, so y1 squared is x to the fourth squared. So we end up with x to the fourth, the negative signs cancel, the integral of e to the integral 7 over x dx, all over x to the eighth dx, Looks nasty, but it's really not that bad because the antiderivative of 7 over x is 7 natural log x. Ooh, I like this. E to the 7 natural log x. E to the x and natural log x are inverses of each other. So we're going to rewrite this using the rules of logs. 7 natural log x is natural log x to the 7th. And again, why did I do that? Because natural log x and 7 and e to the x are inverses of each other. So that just simplifies to x to the 7th. E to the natural log x to the 7th is just plain x to the 7th. So we have x to the 4th, integral of x to the 7th over x to the 8th dx. After cancellation, it's x to the 4th times the integral of 1 over x dx, which we know is x to the 4th times natural log of the absolute value of x. So another solution to this differential equation besides x to the 4th is x to the 4th natural log x.